infinity. Okay, so the subject of infinity categories is a very big one, and I understand you have a whole semester-long reading seminar on this subject. So I just wanted to give you a kind of feeling for the little that I know about it and can explain the motivation a little bit. So this whole subject, in some sense, started about 60 years ago, or even longer ago, and it all comes from two kind of basic themes in homotopy theory. So I'm assuming that all of you know about spaces and the notion of a homotopy. And then once we have some notion of homotopy, which can have different meanings, we have what's called a homotopy category. So let's stick for the moment to topological spaces. So we have here, this is the category of topological spaces. And what we call homotop is its homotopy category, which means that we have the same objects, but only take homotopy classes of maps between them. Now, part of the homotopy theories, that is supposedly what we're studying, the homotopy category. But if you think about it a little more, you see that there are actually things that arise in the original category of topological spaces. We have homotopy invariants there, which we cannot express at all, maybe in the homotopy category, or we cannot show what we mean by them. And the simplest examples are the various limits and co-limits, right? So we know, of course, a product of two spaces is something that makes sense both in the original spaces and in the homotopy category, but any kind of things like a pullback or simple constructions like that don't make sense in the homotopy category. What do I mean by that? I mean that they don't have the universal properties that we expect. So we need to sometimes go back into the original category of topological spaces in order to be able to talk about these things. And these are important, very important constructions that we use all the time in homotopy theory, or co-fibers. And of course, the homotopy versions of them, by definition, are homotopy invariant in the appropriate sense, but they are not something that we can describe just living in this category. So we need to be able to lift things up, look at what's going on here, and then in the end, the answers that we get off, sometimes at least, can be expressed back in this category itself. So that's one kind of dichotomy that we have between the homotopy category and topological spaces. And we can think of that as another way of looking at this same kind of question is the question between discrete or maybe rigid data, let's say, versus, well, we could say continuous, but maybe a better word would be to say approximate. And right, I mean, in some sense, the homotopy, the whole idea of homotopy theory is that we're allowed to change things a little bit, but in the end, being human beings, we need discrete information. We can't really process the idea that it's just or at least we can't mathematically describe something being more or less something. We need to be able to describe it in more precise terms. So let me maybe start with the original example of this situation, which started in the 1950s, so almost 70 years ago, which was the question of what we call H spaces. versus topological groups. So a topological group is something that we understand, and it certainly needs to be described precisely in the category of topological spaces. It's a group object in topological spaces. So we have a product and inverses and so on. And the point is that this has to be strictly associative. We have strict inverses, we have a strict neutral element, and so on. What form does this take in the homotopy category? So of course, we still have, as I said, the product still makes sense in the homotopy category. We can talk about this map existing, but we can no longer say what we would like to say, which is if you take 3 copies of the map and of the space, and then first do the product of the first 2, and then multiply down to x, or first do the product on this last 2, and then multiply down to x, right? So in the homotopy category, we can only say this commutes up to homotopy. There's no language of saying that this commutes precisely. But nevertheless, there is a difference between being a topological group and being an H space. And the example that started this theory off, let's see, I guess you can still see if I write over here, is the loop space. If we take some topological space, and let's call it Y, this will be our X. So this is just a space of pointed maps from the circle into Y, or you can think of them as actual loops. Can you still see that? I guess, yes, just barely. Okay, so this space, right, if we take...
sorry, just to comment, we can still see it up to Y round bracket, so it's fine.
Yeah, so that's as far as you go, right? And if we think of this as actual loops in here, so this is Y, and here is an actual loop going around, we can concatenate 2 loops like this, and that is the operation that we have. This mu that I was talking about, but of course we know from when we first studied the fundamental group that the concatenation of loops is not strictly associative. It's associative up to homotopy. Okay, so that's still something that we can say. In other words, this diagram in the homotopy category of spaces commutes when X is the loops on Y. Okay, but it turns out that, and then, so maybe that's as much as we can say. No, it turns out that there's more than this we can say. There are 2 things that I can point out. One is the fact that there's something called the Moore loops that you may be familiar with, which is, we write it as maps from, let's say, 0, A, into Y. Can you still see that? I guess just barely. In other words, loops which are parameterized by, not by the unit interval. And then we can concatenate such loops and in a strictly associative way. And it's very easy to see that this is actually homotopy equivalent to the original loop space, and it respects the right. It's the same operation of concatenation. So here we see that there is a model which is strictly associative for the loop space. And with a little more effort, or if you're more familiar with the simplicial version of all this, so Dan Kan described a construction that takes a simplicial set, a pointed, maybe reduced simplicial set, and applies to it a G functor, which actually produces a strict simplicial group. And taking this strict simplicial group and realizing it gives you a strict topological group. And it turns out that this is homotopy equivalent to the loops on the realization of K. So this gives us a way to not only make it associative, but actually get a strict units and everything. So it turns out that loop spaces are not just homotopy associative H spaces, but they are equivalent in the appropriate sense to strict topological groups. But the question is, okay, This is as far as we could get in the homotopy category, saying that this is a homotopy commutative. But there are many examples of H spaces which are homotopy associative, but are not equivalent to strict topological groups, and that turns out to be equivalent to being loop spaces on something. So how can we make this distinction? And this was a question that people thought about in the 50s, as I said. And what Stasheff then was the one who came up with this approach. What he said, okay, I can erase this over here, was we not only want the spaces to be homotopy commutative, but we notice that if we look at 4 copies, instead of this very simple diagram that we have over here, if we look at 4 copies of X, of the product of X 4 times, then there are a variety of different maps here into X itself, which come from different ways of writing parentheses, right? The maps over here, if I wanted to describe them in a less formal way, I would say that if I take A, B, C here, what I'm doing here is A, B, C, sorry, the other way around, A, B, C here, and here A, B, C, right? So these are really the 2 maps have their names by what they do to elements. And here, it turns out that if you think about it, there are 5 different ways of doing these things. And I can arrange them in the following way, right? So I can say I do A, B, C, D, right? So here I first multiply these 2, then multiply the result by this, and then multiply the result in this order, of course. And what I can do each time is, remember, we said this was homotopy associative. Let me choose a homotopy that's a witness for the fact that it's homotopy associative. And then I say, okay, well, we have to be careful. Am I doing A to the appropriate H of BCD? I'll write it down here like this. So H multiplied by this. I'm using a mixture of languages just so we get the feel. And then what happens after we've done this? I still have BCD in parentheses, but now the parentheses are written like this. Okay, so that's one thing I could do inside the parentheses, but I could also think of CD as being already given to us, and I'll do H of A, B, C, D. And then what I would get would be to switch the parentheses in this way. Right, so I moved the third thing outside of the parentheses, and I won't tire you with the other 4 ways of doing this. Now that I've done this, I can do the same thing over here. Okay, we'll just take a minute like this. And here I can now say, let me think of AD as multiplied by C and then D. And now when we look at this, we see, here we've done simply D and the homotopy of ABC. I haven't written names for the others too, but you can easily figure them out. Okay, so we do have 5 different homotopies that are induced by the choice of H that we had over here. Remember, the H is not a map taking elements, it's actually a map of spaces. So this can be written more precisely, but you get the idea, I hope, from this. And then Stasheff said, well, if we really wanted to be, if it were really commutative, then going any way around here would give you the same answer. So let's assume, or let's require that in the case where we want something to be a loop space, there better be a way to make the going this way or going this way homotopic to each other. The homotopies have to be homotopic. So we have a fill-in for this. And then we say, okay, so we've gotten from just being things working for 3 spaces, for 3 copies of X to 4 copies of X, but that it doesn't end here. We can go on doing this for 5 copies. And for 5 copies, if you arrange all this information, you get something 3-dimensional in the natural way to describe it. And again, you get something which is described on the boundary of a 3-dimensional polytope by the choices of L and H that we've made before. And then you ask, can you fill in the interior of that? So formally, what we're doing is we're taking the product of this pentagon with x to the fourth and mapping it to x. But we only need to keep track of what's happening along on the pentagon itself. Okay, there are lots of technicality here that we certainly don't want to go into, but this was Stashev's idea, and what he said, he actually constructed a sequence of polytopes like this in all dimensions. They're called associahedra. And he said, if we can get, so one of the things was to convince yourself that in all dimensions we get something which is in fact a convex polytope, in other words, is equivalent to a ball, but then so its boundary is equivalent to an appropriate sphere, and then we get a series of obstructions which and the interesting statement was that if you can manage to find the original homotopy H, it's given that there is some choice for it. You have to make the right choice such that this has a choice of L, such that at the next level you have it, and so on. And we have something which we then can call infinitely homotopy commutative. So we say, oh, in this case, it's well, the diagram is homotopy commutative, but in this case, we're talking about the group structure. It's infinitely homotopy associative. The associativity happens at all levels. And then a separate observation in this case said that if that can be done, well, you can state it in one of two ways. Either say that the original X was equivalent to loops on something, or what Stashev actually did was he gave you a procedure for recovering the Y whose loops are this X. So that was the way they were thinking of trying to classify X, make it a space whose loops are give you back X. And another thing which as we saw here was a completely separate observation that we made back here using other tools was that if we can make it into a loop space, this whole thing can be strictified to an actual associative topological group. So this was the beginning of the infinity category point of view. And the question is, how do we actually keep track of all this information? So you see what's happening here is I said there's an infinite sequence of such polytopes, each of which has the property that its boundary is product of lower dimensional things, so that we can fit in the information we made, the choices we made before into along the boundary of the next level. And then we ask, can we fill it in and continue in this way? So, okay, so what if we go back to what I had here and erased, we were thinking of this picture is something that's happening in topological spaces. But okay, so we can do it just within the category of topological spaces, and you could try. So one approach to all this question would be kind of a model category point of view, that we lift up something that's in the homotopy category with this rather meager information that we have over here, and we add more and more information till we get something which actually gives us something back in the homotopy category, because the information that we get at the end of all this process is that X is weakly equivalent to loops on Y for some Y, and in a way that respects that the mu here corresponds to the concatenation of loops. And that turns out to be homotopy invariant information. In other words, that's something that you can actually say in the homotopy category. There's a way to talk about loops and so on, at least in the pointed for a pointed model category. You can do all this in a pointed model category. Say that you have the loop space. But what you can't say is, given the original X, is it in fact a loop space, aside from someone just coming in and producing Y and showing you that they're equivalent. So this is the theme that started off a whole direction of the notion of operads and so on, which people developed, and it turns out, for instance, if you ask if it's a double loop space, then for a double loop space, as you probably know, the multiplication is homotopy commutative, but then it's not true that the double loop space can be strictified to a commutative topological group, because that would be basically just an abelian topological group is just a product of element mechanics space. So that's something rather rare in real life. And okay, but if whatever it is, that happens for double loops, what about triple loops, and so on. So it's clear that the issues are not always best expressed in this kind of naive point of view, that what we're trying to do is strictify something, make something that existed before that we know how to do in the strict sense, and what is the description in the homotopy invariant terms of that property. For a double loop space, it's being a double loop space, so we can't really say, well, that just means that we have a slightly more commutative H space or topological group. Okay, that's a whole direction that I don't plan to go into, but what it did was show us that probably the question of strictification is not the right way to approach these kinds of questions. We have to have a different language, and but we know something of what we need for that language. Namely, we need to be able to talk about homotopies and higher homotopies and so on, at least in this approach. So what the next step in this process was the notion of enrichment. And this is maybe also to those of you who studied category theory, that is kind of the basic point of view of category theory, is that we study a mathematical setting, a category, purely through the appropriate notion of morphisms, of functions between different things. And for us, the objects are black boxes. We don't care what they are. All we care is to know how you go between them. Now, this sounds a little strange to the way, it's not the way we usually study something like groups or vector spaces. Well, in some sense, vector spaces have that property, right? An individual vector space is very colorless. It's just a certain dimension and determines it completely. But all the work we do in linear algebra is for morphisms between the vector spaces, and more particularly, we see from that example, the self-morphisms, the endomorphisms are really somehow the key to understanding a category. So if we want to take this point of view to something even as complicated as topological spaces, we say, okay, a topological space, you can call it whatever name you want. You have CPN, you have S17, fine. But for me, those are black boxes. I don't care how they actually look, which is not the way certain people originally approached them, but that is the point of view of homotopy theory. We only want to understand maps between them, but it's not enough for us to look at just homotopy classes of maps, because that would bring us back into the homotopy category, and that is certainly inadequate for most of the things we want to do. So we need to be able to talk about not only maps, but homotopies and homotopies between homotopies. So the first approximation to that is something that's familiar to anyone who has studied point set topology, which is the idea that if you look at the set of maps of topological spaces from X to Y, this set has a topology. We can think of it as a topological space with a compact open topology. And then in this set, now it's itself a topological space, the points are the maps, and paths between 2 points are exactly homotopies. So this is a good language for talking about it, but how would we bring in this kind of homotopy between homotopies, gluing together homotopies in a certain way and then choosing a homotopy between them? We see it becomes a little messy just using this topological space. And what, I'm not sure if I think it is basically an idea of Kan and then Dwyer and Kan together, is that the right way to organize it is not to think of this just as some kind of blob, but just as we're used to doing for 100 and more years with topological spaces. We want to have some combinatorial structure to them. So we think of something like a simplicial complex. simplicial complex is something much more rigid than the original space. And as you know, I mean, we can do a lot of things using just that combinatorial, discrete, finite, usually, information. And the whole, simplicial homotopy, homology, and eventually more complicated invariants can be described in that language. But what Dwyer and Kan basically in his thesis, his discovery was that if you want to do homotopy theory for simplicial complexes, you actually need something a little bit more fancy, namely a simplicial set, which is okay. I mean, I assume most of you have seen this notion, and if not, it's not something that can be explained on the. But the basic idea is that a simplicial set is a list of a set of simplices in each dimension, like in an abstract simplicial complex, with, for each simplex in dimension n, we have n+1 face maps, which take us to the simplices one dimension lower down. So I can draw it. Okay, so if I have, let's say, x dot is a simplicial set, then what it is it has xn, the set of n simplices, and now we have n+1, it turns out, face maps to xn-1, the set of n-1. So for each n simplex, I can say, here, if I had something like this, I want to be able to say, here is if this is 0, then the B0 is this face of it in our list. I'm not giving them names, but that's the idea. Here they're just named. Again, we don't think of them geometrically, but just in terms of the information of how we glue one to another. Now, if we use this language, then we can replace, in fact, any topological space. This is something you all know from using singular homology, is you take a space and you actually replace it by its singular set, which is the set of the n simplices here are what people originally thought of as just being a set of rigid simplices inside a simplicial complex. They're kind of more singular simplices where you just, here's your space and you take a map from this into it, which doesn't have to be a straight, simplex, but it could be curved and not necessarily one-to-one. And the set of all these is the singular forms. It's easy to convince yourself that this forms a simplicial set. So if we do that to this over here, what do we get? We get something which is actually our basic example of an infinity category. Namely, I take the simplicial set. So this is now a simplicial set, and what it has in dimension n. So if I call this, let's see, can you still see this? Or is it? Yeah, okay. So we call this m. Then mn will actually be the set of maps from x cross the n simplex into 1. And so, in other words, this is exactly the construction, almost exactly the construction of the singular set in the setting of maps. And again, you see, so if you look at what we have in dimension 0, of course, the 0 simplex is just a point. So we have actually the set, the 0 simplices are just the maps. The 1 simplices are x cross an interval into y. So those are homotopies. And for some reason, a little strange, instead of doing the kind of homotopies between homotopies that we would naturally think of, namely something where here we have H1 and here we have H2 and we have some homotopy between them shaped like a cube, it turns out to be more convenient for some purposes to use a collapsed version of this. So we have H1 here, H2 here, and okay, I'm not trying to be very precise. So this was from F to G, and this was also from F to G. And somehow you cook it up so that instead of using what looks more natural, a square, use a triangle. And the filling is described by what happens along here. Again, I don't want to go into the details of this. I'm sure you'll talk about this later on. Okay, so now we have a good combinatorial language to talk about homotopies between homotopies, and so on. And at the same time, we have the structure of a category. So we have the tools of category theory available to us. And the idea here is that what we do, let's use a different, so let's see. Yes. The idea is that we have here the notion of a simplicial category, which just means a category enriched in simplicial sets. So I remind you, what does it mean for a category to be enriched in something? So it's the usual categories that we always talk about are just categories enriched in sets. The Hom from X to Y is a set. But if you were in abelian groups, the Hom from A to B is not only a simplicial, is not only a set, it actually is an abelian group itself. So then we say we have a category enriched in abelian groups. But a fancier thing is what we have here. That and right here we did the same thing here. We said that the set of maps in topological space from X to Y actually has a topology. Here we're doing something a little different, which is also called enrichment, namely we add on to the original Hom that we had a new structure. So this doesn't have to be in top. We can do it in almost any category where we can make sense of multiplying by a simplex, which is a purely combinatorial operation. So we have an enrichment in simplicial sets. The only connection that we have in our case is that at the bottom level, in level 0, it's the original set of morphisms that we have in the category. But, okay, so when I said that we're allowed to enrich in various things, we do need to be able to do the basic operation of category theory, namely to compose maps. In other words, what we need to be able to do is take maps from X to Y, maps from Y to Z, and have a composition map into maps from X to Z, right? And it turns out, so we need to make sense of this, and we have to have an operation that makes sense in terms of composition. So it turns out that simplicial sets have a big advantage over things like simplicial complexes. The product of two simplicial sets is simply the product in each dimension. They cook up all the complications of triangulating the product of simplicial complexes. It turns out that that's taken care of by the additional complexities of simplicial sets. So this is simply a dimension-wise product. And then you see, again, I'm not going into the details of this, but you see that all the things we would like to do, we have a homotopy between maps from X to Y, and then we have a map from Y to Z. We can compose the homotopy with a map. We can even compose homotopies with homotopies. So this is a way of encoding all of this information. And again, the point of view of category theory is that we don't care anymore what X and Y were. As far as we're concerned, they're just names of things. This could be CPN, this could be S17, but we don't care what those spaces look like. All we care about is what the maps would be in them, but not only the maps, also homotopies and so on. In other words, this is all the information that we have about the original category. So we went in a different direction from what we had in model categories, where we still had the objects and we could do constructions on them, like pullbacks and so on. Here, it's not clear what we would mean by pullbacks, but fortunately for us, if they're homotopy meaningful, then they will have the right effect on the mapping spaces. In other words, the maps into a product will be the product of the mapping spaces. The maps out of a co-product will be again a product. The maps into a pullback out of a push-out will all have that property in simplicial sets. So we don't care what the original thing was. If it's topological spaces or something completely different, we can use just what's happening in this world to understand that something is a limit. Again, using the categorical point of view that we take its universal properties rather than the actual construction. The only construction we actually use in simplicial sets is this one of the product. But we get from it for free these additional structures, the pullbacks in simplicial, and so on. Now, of course, we have to be a little careful here in order, okay, so one thing that we can get out of this is that if we take pi0 of the mapping space from X to Y, that will actually give us just, right? We said the one simplices are, so first of all, we need to be able to define what we mean by pi0 for a simplicial set. But in this case, it's really almost what you think. You need to be in a what I call a Kan complex. But basically, since the one simplices are homotopies in the mapping space between F and F prime, here's a one simplex, and here it's a homotopy between these two things. So to say that we're in the same, that their F and F prime are the same element here is exactly to say that they're in the same component of the mapping space. So it turns out that we okay, and this is the HOM in the homotopy category. So from a simplically enriched category also has a homotopy category. And it's defined in terms of the enrichment. Again, we have to be a little careful, but we're not going into all the technical details. Okay, but now the question is, okay, how do we actually describe all the other structure that we were interested in? Something being a loop space. So some of these things, the loop space was particularly simple because all that we had were products and maps, at least into a product, translated into maps, just into the structure of a product on the mapping spaces. But what if you're mapping out of the product, right? That's what we have to do for to understand that an H space was actually a loop space. We had to map from X to the fifth into X. So, and maps out of X to the fifth is, so, okay, so we see that we may have more structure, but again, it's all describable in the end in terms of the mapping spaces. So it's true that we don't have maps out of the product. If I were trying to map, draw that over here. If I were trying to map from X cross X cross X into X, I can't describe this directly in terms of the original mapping spaces, but I can use the structure that we have, right? Because we have structure maps from X to the third to X. This is supposed to be like the multiplication in here, but I have the projections, and those are part of the structure of this being a product. So I have a language for expressing that a certain element, which I really should just call by something else, is actually a product of X with itself. Okay, again, I don't want to go into the details of here, but the various universal properties that we get for mapping into something allow us to express that certain objects in a simplicity enriched categories are limits or co-limits. So we can do a lot of what we would do in homotopy theory. And in fact, Dwyer and Kan, when they first set up this theory, they said, okay, we have a notion of simplicity enriched categories. There are two questions. First of all, what happens if you had something real life, like topological spaces, or more generally a model category? How do you impose this structure on that? Can we translate it into this enriched language? And can we actually do everything that we would want to do in homotopy theory just using the enrichment? Well, that they took as a kind of axiom. They said, as far as they're concerned, a homotopy theory is a simplicity enriched category up to an appropriate notion of equivalence between simplicity enriched categories, something that they call Dwyer-Kan equivalence. So this was kind of a slightly different point of view than what we, so of course, in model categories, we have a variant of that, which is Quillen equivalences, but those are something much too rigid. And here they had something which, okay, they didn't quite get it all the way through, but eventually that was cleaned up by Julie Bergner about maybe 20 or 30 years later, and there is a notion, so if you'd like, there is a model category of simplicity enriched categories in which the notion of weak equivalence is exactly what their notion was, what we now call a Dwyer-Kan equivalence. Okay, So now we want to kind of shift gears a little. This was the example. We get the feeling, at least, that questions like the question that we had about a loop space, I can, modulo understanding how to deal with these kinds of products, I can describe in terms of the simplicial enrichment. But what we need is more kind of full-fledged theory, and what we also are missing in this, and Dwyer and Kan just started off this notion of weak equivalences that we have between these. We know that for topological spaces, we certainly don't want to talk about, in homotopy theory, we don't care what the actual strict model we had is. We just care what happens up to homotopy. If we replace something by a homotopy equivalent space, it should have all the same properties. And the same thing should be true for a simplicial category. We don't want to be rigidly stuck with a certain enrichment, which doesn't allow you to move left and right. We need to be able to be a little more flexible. And okay, there's one more point maybe that I should make, which is the connection with model categories. There they had a real nice insight, which was that, and it looks like it couldn't be true when you first think about it, but it turns out that it is true, that if you started out with something like topological spaces, and okay, so in general, we start out with a model category. And inside the model category, all we do is specify the class of weak equivalences. They said there is a way to construct a simplically enriched category, a procedure called the hammock localization. It's not exactly a localization, but anyway, it's they construct from this a simplically enriched category. Let's go and let's say x, such that, okay, for every x we get a homotopy category. I didn't say that aside from getting the homotopy class of maps, you still have, it respects the composition. So this is actually, from any simplicity enriched category, we get an ordinary category, which is the pi zero of it. So that this is equivalent to the homotopy category of the original C that we started with. And the construction, so in other words, if you only know what the set of weak equivalences is, you don't know any of the other structure. It doesn't, in fact, they later said it doesn't even have to be a model category. In fact, the W doesn't even have to be a set of weak equivalences. Any set that we take, we can do this construction, and it gives you a simplicity enriched category, which has the, in other words, so what do we really mean here? What we mean somewhat informally is that we invert all these elements. The weak equivalences are inverted, and so in some sense we could write this imprecisely as C with W inverted. They use the notation like this, but there are set theoretic problems to just actually inverting this class. It maybe gives you something like the same problems that we have in model categories, but they said, okay, it doesn't matter. This is what we get, an actual construction which is well-defined and gives you, and has the effect of inverting the class of weak equivalences again. So, by the way, here we could end our talk because this is the simplest, the poor man's version of infinity categories. Is simply a category with a class, a specified subclass. This is one.
Sorry, David, I have a question. X is what you, after you inverting the W, or
no?
Or you
so
mean?
Here, this is, I'm writing in parentheses. What they actually did was they produced a simplicity enriched category. That was the thing they produced. They give you a category with the same objects that you had before and simplicity mapping spaces. And the composition is strictly associative, everything that you want. It's an actual simplicial category. In other words, for every two objects that you had in the original thing, you have a simplicial set of maps between them.
Okay,
which,
okay.
I don't have to go into it. I'm sure you'll talk about it at some point. But so here is something that tells you the kind of the minimum that you need to be able to talk. And then so this was then later, many years later, was given the name of a relative category. And Dan Kan, one of the last things he did together with Clark Barwick was to formalize all this, actually set up a model category of relative categories that turns out to be equivalent to the model category of simplicial categories that Julie Bergner later set up. Okay, but so this is just an aside, and so if you want to have kind of just an intuitive feeling, but maybe a very bad intuitive feeling for what infinity category is, it's really having such a thing, a category with a set of morphisms which we want to invert, right? So the point is they have to be something like isomorphism, but if they were strictly isomorphism, they would already have inverses and there would be nothing to do. So, right, the simple example is, say, topological spaces and spaces which induce isomorphisms in homology or in homotopy groups or something. So it doesn't mean that there's a map in the other direction even, but they do have some of the properties of isomorphism. That's literally one. Okay. So what? So now we have kind of two candidates for the notion of an infinity category. And this is really cheating because this is just telling you that from this information we can construct a simplicially enriched category. I always say that the simplicially enriched categories are the ones that give you the actual intuition for what is going on here. It's a way to be able to talk about homotopies and higher homotopies and make meaningful statements about this. In particular, one of the things that we can do, and I'll maybe get back to it a little later, is make precise what I said about loop spaces. So what I said about loop spaces is that they are infinitely associative H spaces. What does that mean, infinitely associative? It means that, okay, they first of all have to be associative in the ordinary sense. There has to be homotopies for those pentagons showing that the fourfold associativity is consistent whichever way you do it, and so on. But how do you actually encode and so on in some formal way? So for the original example, Stashev just cooked up these polytopes, which again, in higher dimensions are not something we can really work with, but okay, he gave a description, he showed that they have the right properties. But what about if we have another question where we want to say that something is, for instance, infinitely homotopy commutative? Or even this more weirder thing that we had for double loop spaces, which were not infinitely homotopy commutative, but had something in between, which also goes up step by step and in the end gives you a double loop space. So there are a lot of issues where it's very hard to keep track of what we're doing. It for those questions, the language of operands is a good solution, but it isn't a good solution for more complicated things that can arise, or more general diagrams. And that is something that we can describe in the simplicial language. But before I get back to that point of view, I want to say something about other ways and maybe nowadays much more popular ways of talking about infinity categories. And that is basically the various notions of a nerve. How do we encode an ordinary category? So, okay, let me now leave all this aside for the moment. And let's just think of an ordinary category C. So an ordinary category, what if I wanted to describe it in diagrammatically? So a category C is described by, okay, here we have the class, or let's assume that it's a set of objects. Just for a moment, let's make a small category. Then we have the, well, it's overall, it's a class of maps, but for each of the maps, any map is a map from something to something. So we have a source and target map into the objects. And we also have a map in the other direction, which is the identity. It sends any object to the identity morphism that we have over there. Okay, now this isn't enough, right? We need something else, which is to say how we compose maps. So we say, if we have a product of n with itself, we have two trivial things that we can do. We can project onto the first, we can project onto the second, but we have also something interesting we can do, which is, maybe I should call it composition. Over here, right? We have the composition. That's something that that has to, I hope this is visible. I see this is not a very good product. The product of n with itself, right? But yeah, right. So yeah, just a second. Yes, of course, as lucky that I have an audience here, we have to have matching morphisms. The end of one has to be the start of the other, but this is exactly given by the source and target over here. So I take the pullback of these two maps, and that is really what we're taking to map into n for the composition. Okay, so this is all, if someone is giving you a category and he gives you this diagram, he has produced a category, he has specified a category, but then you can say, okay, but maybe he just made up what this composition is and it's not associative. So how do we know that it's associative? Taking this information, we now can generate more complicated information, namely the threefold copy. And now, okay, so now we have the three projections, the various projections, omitting the first, doesn't matter. But the point is, we have only, well, in real life, if it is a category, there's only one map, which, there are two maps that we can get over here. We can compose the first two and leave this one in place. Or we can compose, so we can compose times one, or one times compose, the same thing that we did for the H space that we had before. But if we go further down.
Sorry, excuse me, I just have a question. So what does mean this notation product over O?
Oh, okay, yes, that's a good question. So what we're talking about is simply the pullback. We take the two maps that we had over here. These are just sets, right? So what is this? The pullback equals the set of, let's say, M1, M2 in the product, which is what I had at the beginning, such that S, the source of M2, equals the target of M1. Right? That is what we call the pullback of, or sometimes it's called the fibered product of these two things. It's the compatible pairs of elements according to the two maps that we've specified over here. And yeah.
Okay, thank you.
Yeah. Okay, so this is something that the person who produces a category, as a first approximation, he just gives you this information. But if you challenge him and say, I don't believe this is a category, he has to continue back here and show you that these two compositions are the same. And once he's done that, he's out of the woods. He has produced a category and we can't argue. Right, of course, there's also the rules for the identity and so on. I'm not writing everything down, but the basic thing is we have a diagram of this form. If you can see that everything that is supposed to commute commutes, he has, the person who produced this gave us a category. But, okay, so this is what happens. And now we can take two different points of view. So by the way, this construction that we have here is just what we call the nerve of the category. It turns out that this itself is a simplicial set. These are the zero simplices, the one simplices, the two simplices. And you see that they have the right number of face maps, and they also have the right number of degeneracies going in the other direction. So, and you can continue this as far as you want. You just take longer and longer compatible things. But once this worked out, the rest of it just comes for free. We don't even have to verify that it works. And that's what we call a two co-skeletal simplicial set, because it's determined by its two co-skeleton, 0, 1, 2, and then everything above that is just determined by what we have down here. So that is the nerve of a category, which I hope you've seen, is this thing thought of as a diagram in sets, in other words, as a simplicial set. But the nice thing about it is that this actually gives you a way to describe enriched categories. The only thing that you need to do is a category, so sometimes we call it a category object in V, whatever that is, in our case, in simplicial sets, will have all of this information, but all of these things will be simplicial sets. In other words, you'll have not, well, so you say, why is this a simplicial set? This is just a set of objects. Yes, so you're right that this one we would probably want to just be a set, but these would actually be simplicial sets. Okay, so first of all, it gave us a way of doing this, and we can specify, okay, we can say, yes, this is a simplicial set, but it's what's called a discrete simplicial set, one in which is just a collection of points with no non-degenerate higher simplicities.
So are you requiring, like some people in enriched categories require a category to have a notion of underlying set? Is that what you?
So I said something about that. From our point of view, we don't need that. In most cases, right. So when we said it was enriched in simplicial sets, we naturally had at the very bottom level the ordinary set. And for topological spaces with enrichment in topological spaces, if you forget the structure, you get the enrichment in ordinary sets. But you could also have something which doesn't have, right? It's legitimate from our point of view that you don't have an underlying category at all. You just have something with this structure. You're right. There are two ways of thinking of enriched categories. But this is the important one for us. Okay. Now, I guess we should be finishing up. So what is the rule here? Should we just finish up quickly or take a few minutes? What do you want?
Yes, usually we have seminars which last 1.5 hours, so you have at least half hour more.
Oh, okay. Well, I don't know if you want to listen to me for that long, but I will. So I'll continue a little further with this point of view. Okay. So once we have this picture available, we can take two different points of view as to how we could kind of relax this picture a little. And that is, in some sense, the point of view behind infinity categories. So simplicially enriched categories, on the one hand, they are a version of infinity categories because that's one of the canonical models for them. So it's perfectly okay to think of simplicity enriched category, of everything that we say about infinity categories in that language. But the reason they're not so popular nowadays, and you'll hear more about the other models, is because they don't, it's complicated to talk about what is really the heart of infinity categories, which is the ability to relax the strictness that we get for simplicity enriched categories. The way you describe that something happens after homotopy is very convoluted. And it's possible, and I hope to at least get to that point in a bit. So we can do everything we want in this setting, but in some sense, it's not the most natural. For me, it's most intuitive, but it's not the most natural. And so, okay, so now we can go in two possible directions. From this point, we can go into something that we have called, oops, okay, I hope this is visible, Siegel categories or Siegel spaces. And the other direction is quasi-categories. And they involve relaxing something in what's going on here. So one thing that we can say, okay, so single categories, it takes the point of view that what we really want to talk about is simplicially enriched categories. We want to have a simplicial enrichment, but we don't want necessarily to have a strict simplicial enrichment. As I said, the fact that the simplicial enrichment is strict is, from one point of view, for maybe our ease of getting into the subject, is a plus. But from the point of view of getting to the heart of the matter, the ability to relax things, it's a minus, because we can't say, okay, it's just more or less the composition works. So how could we do that if we did what I said over here, namely, think of this as a category, as a diagram in simplicial sets, but we want to relax things a bit. So we could go in a number of directions, but the direction that Siegel went in, and actually Dwyer and Kan also had a little bit to do with that, was saying, yes, I do want to have a strict, so part of the thing is that we have to work with strict things. If we're mathematicians, we have to be able to say something precise. We can't just say, you know, okay, it's more or less like this, or it's homotopic to this, that, or we quickly lose track of that. So we need to have strict structures. They can be complicated, but they don't have to be rigid in the sense that this is rigid. So how does that happen for a Siegel category? What Siegel said, and he was actually used this as a way to describe loop spaces. Way back when people were doing loop spaces as their central issue, he said, okay, maybe I'll talk a minute about that example because it's a little easier to understand. If I try to do this thing for a loop space, how would this look, right? Remember that a group is a special case of a category. A group is just a category with a single object. Okay, so let's think of a loop space or an H space as also a simplicial category with a single object. So again, we erase the actual object that we're talking about. We only talk about the maps. Okay, so he said, fine, here I'm going to construct a simplicial space. In other words, a simplicial object in topological spaces, or if we like, in simplicial sets, because simplicial sets and topological spaces have the same kind of information. So at the bottom level, we'll just put a point, right? We don't even have a set of objects, we just have a single object. So I'll just put a point over here. And at the next level up, the morphisms are just the loop space that we have. So these are, nothing interesting is happening over here. This is just the loop space itself. We think of it as, right, if it's a group, then the elements in the loop spaces, they're loops, right? They're actual maps from the base point back to itself. So either topologically or as a group, the elements of X are supposed to be like the morphisms in the category with a single object. And okay, so here we could do the same thing over here. Now here, right, the reason I wrote before with just an ordinary product is because in this case, there isn't any pullback. Any two things start and end at the same point. So I would just use the ordinary product here. And here I would have the multiplication map and the other two projections that come for free. So far, so good. But now when I get to this, which is X cross X cross X, yes, I have the different maps here, but they don't satisfy the simplicial identities, right? Because it's not true that that multiplying A times B and then times C, or A times B times C, gives you the exact same thing. They're just homotopic to each other. And if we start making this a simplicial object up to homotopies, we won't get out of it. It'll just become more and more complicated. So what Siegel said was, I'm not going to go this direction. I'm going to call this thing X1 because this is X0, which is just a point, so it doesn't really exist. And here I'll just have something called X2 and something called X3. It'll be an actual simplicial space, or more precisely a bisimplicial set, a simplicial object in simplicial sets. But how will I recover the information that I had before? He said, well, we still have with these two maps, right? The two outer maps that we have over here, this one and this one, give us the two projections. So if I take it from here, from these two maps that I have, let me just erase this and we'll remember that that was what is supposed to happen, x2, x3. So we said from the two outer maps that we have here, which are supposed to be like the projections, I can produce a map P1, P2, this is P1, P2, into x1 cross x1, right? So I have a map from x2 into this product, and what Siegel said was I'll require this to be a weak equivalence. This is called a Siegel map. And now if you actually track down what's happening over here, there are, using just the far away maps which don't involve the product, which are just projections, by combining them in various ways, I get a map from here into x1 cross x1 cross x1, and I require that to be a weak equivalence. This is the next Siegel map, and the next Siegel map. So he had the right idea that instead of, I will require to be a strict simplicial set, but the actual space of maps, so to speak, won't be a strict product. It'll just be weakly equivalent to it. So I can still use all the simplicial identities on the nose, but I relax the fact that it's not the actual product. And what he showed in this example of the loop spaces is that if we can produce such a simplicial space, we can actually realize X. Actually, you just take its topological realization, and that classifies the loop space, gives you D loops X1. But, so this was Siegel's idea in the context of loop spaces, and Dwyer and Kan with Jeff Smith came along a little later and said, well, you actually don't need this to be just a single point. This could be just something which is homotopically discrete. In other words, it's like, instead of having a set of objects, because we want to describe things in homotopy invariant terms, I'll just say like these were weak equivalences. This will just be weakly equivalent to its set of components. It'll just be a disjoint union of contractible simplicial sets. So and then we've immediately generalized from the case of a group to, or monoid actually, to a category. And this was the idea. Now, it turns out that there are two slight complications you need to do. There always are technical points. You need rules to make this really behave like a category. So there are these two variants called Siegel spaces and Siegel complete Siegel spaces and Siegel categories that have these that have the right additional technical requirements. But this is the basic construction. We have, so it's closer to simplicial categories. And of course, if you had a simplicial category, you would get a strict thing like this. At the bottom, you would put the set of objects, a small simplicial category, a set of objects, and then you would do just what we said over here. So of course, yeah, if we replace this by a general x0, we have to go back to what was pointed out here. You have to do this, has to happen over x0. And there are many variants of this that we could go into. So this is Siegel's idea of relaxing the notion of a simplically enriched category. And this is a perfectly good way of doing things, but there's also another thing that we could do, and that would be to say, okay, at the bottom, I have this nerve, and we said in the nerve, we just have
sorry, there is a question on the chat. Okay. Choosing a Hopf algebra is okay for xi.
Say that again?
So the question is, choosing a Hopf algebra is okay for xi. So feel free to unmute to discuss this question further.
Sure. Why don't you just ask whoever had the question?
So, I mean, I was just wondering if it is okay to choose a Hopf algebra for xi, because if we have a Hopf algebra, then we have a map from the Hopf algebra to its tensor product with itself. So the diagram you draw resembled that because of that.
Yes. So this idea of describing categories by a diagram like this, I'm not sure if that's exactly what you meant, but the notion of a Hopf algebroid, which is described exactly in this language, it allows you to do a lot of things. So here, what we were doing, right? We didn't. When I said that we could do this for topological groups. Of course, for groups, we have something in addition, right? Because we can, for instance, have the trivial element, the neutral element in there. And in a Hopf algebroid, we have a same diagram, but we have also a groupoid structure. It's supposed to be like a groupoid object. And then we have this additional thing that we can switch these over, right? The kind of antipode. Yes, so this is a language which is convenient for a lot of things. And you're right, that was the way people set up Hopf algebras, which were originally described by just a lot of messy diagrams. This was kind of a clean description. But let me get back to the case that I wanted to talk about, namely the quasi-categories, the other point of view. So the other point of view would be to say,
Thank you.
well, we want not to go up a level into simplically enriched categories. We still want to stay in sets. But what if we try to look at the nerve of a category, and we so this is just an ordinary set, and this is a set and a set, but we don't want anything to be very strict. We don't want we don't even maybe want the composition to be uniquely defined. Sounds like a very strange choice to make, but it turns out that that was the right idea. By the way, this idea first came up again in the context of infinite loop spaces in work of Boardman and Vogt many years ago, about 60 years ago. They came up with this idea of a quasi-category. So let me do it over here. Okay, so we understood what this is supposed to represent. And now what we want to say is, how do we, what is really going on if I want to describe the composition here? So the composition tells me that if I have, so what is an element in here? Is this still visible? Yes. So what is an element in here? If we want to draw these as, right? So these are the zero simplices. Good. And these are the one simplices. So we think of them as being arrows. I want to draw them in a right, and they are one simplicity. So in our what will eventually be a quasi-category, we start, this is x0, this is x1. It is a strict simplicial object. We have all these things going back and forth. So we have the what is secretly we think of as being target and source, and the degeneracies give us the identities. All of this exists. At this level, there's no difference between a strict and a non-strict version. We have objects and we have morphisms, and for each morphism, we have a well-defined source and target. The question arises when we want to do composition. So here we said, okay, for every pair of arrows where this ends, where that one begins, right? That's exactly the target for this one is the source for this one. I wrote them in the opposite order. I have a unique arrow that comes out of it. But if we want to take seriously the point of view that this is a two simplex, then a two simplex, okay, what do I have? I should draw this in two different colors. I have this pair of arrows. I have information down here, and I want to describe something up here. But what I'm going to describe is not just the composite of them, but a two simplex, right? So if this is A, B, C, those are the three objects that we get over here, and these match up along here. I want to be able to say, I can compose them, but I don't necessarily say there's a unique composite. I can say that maybe I can choose one or the other composite that could exist, but I have to give you in some sense a homotopy between the actual composite, or maybe better say the formal composite of this, which is just concatenating them, and the simplex that we had over here. And that was an idea that actually went back to Kan's approach to homotopy theory of simplicial sets. He said this was the famous Kan condition, which says that if you have this horn, which is just part of the boundary of a two simplex, in this case, the boundary without one edge. To say that you have a complex means that you can fill it in. But we don't require that the fill-in only has to happen in our case when the arrows are composable. In other words, if I try to look at something like this, there's no reason why I would get an arrow here, because that would be saying that I can decompose F, let's call this F for the moment, as G composed with something for any G. Now that is too much to hope for. But so this we don't want to have a fill-in for. But we do want, if the end of one is the starting of the other, we do want to be able to at least choose some fill-in for this. Okay.
So I have a naive question here. So
Yeah.
if we don't require a unique composition of two morphisms,
Right.
it rather means that every two compositions will be homotopic in whatever it means, right?
Right. So that's right. That's the next point, right? If we just said that there is some way to compose them, then we would never get out of this. It would just become, it wouldn't be describing anything meaningful. So what Boardman and Focht originally said, and then other people took this up, was that yes, okay, you can take this point of view, but you have to take it in all dimensions. So what would it look like in the next dimension up? In the next dimension up, we would say, well, let's say that I had, let me try and see if I can draw this picture like this. So here I have H composed with G. And here I have, I want to think of another thing as being H composed with G. So I'll just repeat the H twice. And I'll say, okay, here is my F that I had over here. And here is the witness for it. So the thing that we fill in here is in kind of intuitively, we think of it as being a homotopy between the formal composite and our chosen new composite. So we have a new composite plus a homotopy to a formal composite. Okay, but we could have a different formal composite, namely, I'll try to do it back over here, right? The one that we had over there is maybe a different F, let's call this F prime and this F, and its own homotopy between the formal composite of F and G and this new choice. So we have F and F prime as two different choices. But notice that this back edge over here has both of these are the same H. So here I have not only a formal choice, but I could actually have here the identity, which means a degenerate simplex, and the degeneracy of H itself. In fact, this is the role played by degeneracies. They give you kind of the trivial homotopies between something and itself. So I hope this is not too messy a picture. I have a third of the four faces of the tetrahedron that I'm drawing here. Two of them were choices, the blue and the red, two different choices for the composite of G and H. One of them is something purely formal, namely this degeneracy, which has the identity homotopy between H and itself. And now I'm in the same situation as I was before. I have the boundary of a tetrahedron with one of the faces, this back face that you don't see here, missing. And the rule now tells us, yes, we're allowed to fill this in. So we both get the back face, which will give you a homotopy between F prime and F, but we'll also get a witness for that homotopy, namely the fill-in for this simplex. So this is the notion of a quasi-category where nothing happens strictly. It all happens up to certain things, but when we up to homotopy, but we always have to specify the homotopies. And this, in some sense, is kind of the heart of the infinity point of view. It's more conceptual, but it's very hard to work with. So it's good for kind of the bird's eye view of the subject, but to actually understand what's going on, I always find one of these other two cases a little easier to get your hands on. But the point of view that we take here is that rather than saying that something strictly commutes, we don't even allow that language. I mean, there's no way of saying that F is the composite of G and H. There is no one composite. We can choose a lot of different composites, but any two choices have to be coherent in the sense that they are not only homotopic to each other, but all the homotopies involved here, the blue, the red, this new one that we get at the back, are coherent in the sense that we have the fill-in of the thing itself. And this continues in higher dimensions. So if I now have two different fill-ins of the inside here, they will also be coherent one dimension further up. And this is a good exercise to see that you understand it, just to play with the simplicities to see how this language allows you both to say that composition is well defined up to all higher coherences, but also to say that composition is associative up to all higher coherences. Because if we have a three maps now, I have a picture in mind, it doesn't matter. Let's say I have F, G, and H, which I want to compose. So, okay, I've chosen a way to compose these. I've chosen a way to compose these. So this is really, this arrow back here is like GH. I'll just write it as GH. This arrow over here is FG. And now I can compose FG with H and get this one over here. Or I can compose GH with F and get something. And what I'm saying is, okay, these are various different choices, but they'll be homotopic. The fill-in will say that they are compatible with each other. So yeah, you just have to sit down and draw this picture for yourself and figure out the choices that were made in specifying that this is a composite and that's a composite. They come with the fill-in simplex, and then we. But the fact that we want to make it associative gives you another couple of fill-ins, and then you're in the situation that all but one face is given to you, and then you can fill it. Okay, so I think this is okay. Yeah, one last thing. So here is maybe a quick summary of what I'm sure you'll go into in more detail. On the one hand, we have simplically enriched categories. They are somehow the most down-to-earth version. We have homotopies, higher homotopies, everything. We know how to compose them. And we have to work to express the fact that something is homotopy commutative or whatever. But we have the language available to talk about higher homotopies in simplicial categories. Then we relax that in one direction. We still think of this as being like simplicity enriched. We have the simplicial set of maps, but we no longer require the composition to be strictly associative. So those are the two Siegel versions of infinity categories, where again, it gives you a global picture because you have the set of morphisms and you have the rule for composition. That's just this map mu here in the middle. There isn't choices of how you compose things, but making things coherent involves things which, well, yeah, it's not really, because you need to invert this Siegel map in order to take a choice of elements and compose. Sorry, I wasn't being very precise there. It's not equal to this, but it's weakly equivalent. But if I choose globally one and inverse to this, then I get a way to do compositions globally, which I didn't have in a quasi-category. Quasi-category is the most lax version of everything. I can no longer do anything precisely, but I have the point of view that encoded into this, everything always comes with all the higher coherences that we need. So we only talk about a diagram if it's already equipped with all the higher coherences. That doesn't let you do a hands-on version of this. So in the just few minutes that you've given me, I want to explain a little bit about how we do that. How do we use, in the world of simplicial categories, how can we talk about coherent diagrams? Because, by the way, Dwyer and Kan, who set this thing up, as I said, maybe 40 years ago, did set up not only the notion of simplicial categories, but they were kind of predecessors of this more modern way of looking at it. And they said, yes, we also want to be able to talk about homotopy coherent diagrams. What does that mean? So what they said is, I won't have time to really write down the details, but let's say that we have a certain diagram here, a strict diagram, okay? so here is F, G, H, and now here is G composed with F, and here is H composed with G, whatever, wrote in the wrong order, and then all the way over I have F composed with G composed with H. So okay, so this is some strict diagram, and I want to be able to talk about a coherent version of it. So, okay, I certainly have to choose where I'm going to send F, G, and H. But if I'm going to be talking about a coherent version, I don't have the composite. I mean, I have two separate things. I have F, G, and H. I have the actual composite of these representatives, but I'm not saying, so here's the way you should think of it. I make a choice of F, G, and H, but I also have to make a choice of all these other maps that you see here. And it isn't necessarily possible to make the same choice for this to be the composite of these two. But what I can do is fill it in by simplices here. So here I'll put it in quotes. This is not the actual composite of G and H. It's a representative for that composite. So you see, I'm really coming back to the same description that we had in quasi-categories. The point is that for Dwyer and Kan, they said, yes, this we can describe in the language of simplicial categories. I think the original category was just an ordinary category. I can always think of an ordinary category as a simplicial category by thinking of the simplicial enrichment as being discrete. If I do a cofibrant replacement for this thought of as a simplicial category, so that we need a model category, I'm sure you'll talk about that at a later stage, then a map of simplicial categories from this cofibrant replacement into whatever category we're talking about, top, or whatever category that we have with a simplicial replacement, is exactly this thing here, a functor from here to here of simplically enriched categories, is a coherent diagram because it doesn't choose necessarily F, the thing corresponding to this, to be F composed with G. Why not? You say, why are you making it complicated? Because it could be that F composed with G is also M composed with N, right? This same composite could be decomposable in two different ways. And there's no way I can guarantee that the representatives for M and N will compose to the same map as these representatives. But if I have a homotopy commutative diagram, then they'll both be homotopic to whatever choice I make over here. So I can choose homotopies for these things. And that is always possible at the first level. And then if I can do it further up, then I've chosen all the coherences. And their main theorem in this context says that if I can choose this, then I can actually strictify this diagram. Okay, I think that gives you something of a feel for what this area of infinity categories, what it does, and I understand you'll be going into more detail on all the different models and how to use them. So good luck to you with that. And is there any questions?
Okay, yeah, okay. Thank you very much. Thank you.
Good. So
yeah, any questions? Okay, we thank Professor David Blanc again. Thank you very much for this. Okay. Okay, that is. See you. Bye.